Thank you.
Thumbs up. Check the second one.
So, can you put this computer to the side screen?
To the side screen.
Yeah, thank you. Okay, thank you, sir.
Okay.
Appreciate it. Thank you.
This one comes up on HDMI. Let me see. Okay. So.
Thanks a lot, sir.
So this one.
Yeah.
Switch HDMI on.
Okay.
Okay, comes up.
All right.
So one PC on this one.
I want this one. No,
Okay, sorry.
Not the PC, the visualizer.
Okay.
Yeah. Okay. Thank you, sir. Thanks, sir. Have a good day.
Okay.
All right, guys. Sorry for the delay. So, just one announcement. The quiz number 2 is due by 11 a.m. this morning. If you haven't done so, please do so before 11. You got just about less than an hour to complete quiz number 2. And right now, the thing this is week 3, right? So we are in week 3. So I asked you guys to watch these 3 videos. There are 3 videos. There's a video on central limit theorem. There's a video on chi-square distribution, and there's a video on student tree distribution. So I will go through them quickly as possible. All right, and then do some examples as usual. All right, the first thing is the central limit theorem says the following, that if you have a random sample from a population with mean mu and variance sigma squared, then this guy here approaches the standard normal distribution as n approaches infinity. And this is the sample mean, this is the population mean, and this guy is known as the standard error, right? So a model based on the central limit theorem. So this is what I just said. Now usually you can never have an infinite sample size. So you need to assume that this is approximately equal for a given n large enough. Usually in statistics we take anything greater than 25 or anything greater than or equal to 25 as a large sample size. Right? So if n satisfies that, then you can assume that the left-hand side is the same as the right-hand side. And doing some math, you will get to this stage here, right? So this is the approximation based on the central limit theorem, right? Now, one example I looked at last week. Remember, I looked at this example on Friday last week, where we wanted to calculate the probability that a binomial variable with these parameters is between 100 and 200. Now, it turns out that this probability is equal to this, which is nearly impossible to calculate even using a calculator or a computer, because you have 1,000 factorial, which is almost impossible to calculate even on a powerful computer, right? So in order to compute this probability, you can use the central limit theorem. And that's what I showed in this slide here, right? So I'm going to use the fact that, okay, the sum of the x, here we are assuming x1 to xn are Bernoulli with parameter 0.2, which means that the sum is a binomial. So using the central limit theorem, which I just talked about, you can approximate this probability by this probability using star, which I just mentioned a couple of minutes ago. Star is the equation, is this equation here. This equation is known as star. Okay, this is the equation star. So using that, you can approximate this probability by this, and hence you can compute the probability that the binomial variable is between 100 and 200 by this probability, which you can read from the tables for the normal distribution, right? Okay, so this is what I have done here, right? So first you need to work out the mu, which is the mean of the Bernoulli population, sigma, which is the variance of the Bernoulli population, and sub them in here in place of mu and in place of sigma, and then you get to this and you get to this, and you can calculate this using normal table, right? So that's the CLT. I hope the second video I asked you to watch is the sampling distribution is a distribution that arises as a function of the data, right? When you have a function of the data and that has a certain distribution, then it's known as the sampling distribution, right? So there are two sampling distributions I wanted to talk about. The first one is known as the chi-squared, right? And this is the PDF of the chi-squared, and it takes a typical shape looking like this. There's only one parameter a, which is known as the degree of freedom parameter, right? The R commands for the PDF and the CDF of chi-squared are this and this, and DF denotes the value of the degree of freedom parameter, right? The percentiles of chi-squared are denoted by this, right? And what this means is the area to the left of this is equal to alpha. So you see the area that I have shaded here is equal to alpha. So the area to the left, or the area below this point, is equal to alpha, right? And these are two examples on how to read the values of the percentiles using the table. And this is the table I'm talking about, this table here, right? And if you had watched the video, I showed you how to read the percentiles, right? And then there are some properties of chi-squared. So if you have a variable x that has a chi-squared distribution with a degree of freedom, then the expected value is a, the variance is 2 times a. And if you have a random sample from a normal with these parameters, then this guy here has a distribution that is equal to sigma squared times the chi-squared variable with n minus 1 degree of freedom. And this property is exactly why the chi-squared distribution is is a sampling distribution, because on the left-hand side of this equation, you have a function that is a function of the data only, right? The left-hand side only involves the data, whereas the right-hand side involves the chi-squared variable, and hence the chi-squared variable or the chi-squared distribution is a sampling distribution because it arises as a function. It arises as the distribution of a function of data only, right? Okay. Now, another property is that if you have two independent chi-squared variables, then their sum is also chi-squared with the degree of freedom equal to the sum, a plus b, right? And if you have a variable that is normal 0, 1, then the square is chi-squared with 1 degree of freedom. Okay. The final property is that if you have independent normal variables like this, right, then this guy here is chi-squared with n degree of freedom. Now, there is a lot of people confuse. Let me show you. A lot of people confuse this property, and you see both of them on the side. A lot of people confuse this one with this one. These two are two different properties. Here, you're taking the deviations from the sample mean. And here, you're taking the deviations from the population mean. So these, although they look similar, they are not the same, right? So when you take the deviations from the sample mean, this guy has a chi-squared with n minus 1 degree of freedom. When you take the deviations from the population mean, which is mu, this has a chi-squared with n degree of freedom, right? So these two are different properties, right? Okay, guys. The last video I asked you guys to watch is the student state distribution. That is also a chi-squared distribution. The PDF is given by this formula here and is defined from minus to plus infinity. A is again a degree of freedom parameter, and it takes positive values, right? The shape, if you plot the shape, the PDF of a T distribution with a degree of freedom and the PDF of a standard normal, they will look similar. I mean, in the middle, they are all similar, but the difference is that is in the tails. In the tails, the PDF of the T distribution, right, is thicker than the PDF of the normal distribution, right? As you can see, it has thicker tails on the left and also on the right. So for this reason, the student's T distribution is known as the heavy tail distribution because it has thicker tails than the normal distribution. And the normal distribution is a light tail distribution, right? Whereas student's T is known as heavy tailed, right? Okay, right. The R commands for the PDF and the CDF of a T distribution are this and this, where DF denotes once again the value of the degree of freedom parameter, right? And once again, the percentiles, if you want to read the percentile of a T distribution, this is the equation that defines the percentile. So once again, it's the point below which there's an area of alpha, right? Below this point, that is this area here, has an area of alpha. And this point here is known as the percentile. It's known as the percentile of a T distribution with a degree of freedom. So once again, there's a table. There's a table for reading the percentiles of a T, and I showed you in the video how to read it. So this is the table for reading the values of a T distribution, the percentiles of a T distribution, right? And finally, the properties of a T random variable are these. The first property is the expected value of a t variable is 0. The variance is a divided by a minus 2. As a approaches infinity, the t variable approaches the standard normal variable, right? And property number 4 says that you should look at the ratio or the quotient of x bar. X bar is the sample mean divided by s by root of n, where s is the sample standard deviation. Then that has a t distribution with n minus 1 degree of freedom. Now this is an important property because it explains why students t is a sampling distributions. Because if you look at the left-hand side, it involves only the data. There's nothing but the data. It's a function of the data, right? And the right-hand side is a distribution, which is the student's t distribution, right? So you see it arises as the distribution of a function that involves data only, right? So hence that explains why student's t is a sampling distribution, right? So these are properties I would like you to know. I mean, and this is an example I did. I hope you guys looked at this example, right? I will do more examples in a minute, right? So the first example I'm going to do now is the following. Example 1. Right? So suppose right. IID, by the way, if you don't know what IID is, IID means independent and identically distributed, right? I hope you know what it is. So we want to find the probability that you have a random sample from a Poisson distribution with parameter lambda, and we want to find this probability. And so obviously we need to, because this involves the sum, one way we can do this is to use the central limit theorem, right? So that's what I'm going to do. So the first thing I'm going to do is I'm going to divide everything inside the brackets by the sample size, n. So this will become the probability that a divided by n less than or equal to x bar less than or equal to bn. Right. Now the central limit theorem, if you go back here, let's look at the computer here. It says this. This is what the central limit theorem says. Is x bar minus mu divided by sigma by root of n, right? So we need to first find out what mu is and what sigma is, right? So remember, mu is the population mean and sigma is the population standard deviation. So in this case, the population is a Poisson population with parameter lambda. So your mu is the expected value of xi, which is equal to lambda, right? And your sigma squared is the variance of xi, which is also equal to lambda, right? So sigma is the square root of lambda. So let's put this in a box. Okay? You see why I've done this? Because I want to use the central limit theorem over here, right? So now in the middle, I'm going to subtract the mu, which is lambda, and divide by square root of lambda divided by square root of n. You see why I'm doing this? Because I'm using the central limit theorem, right? Okay, so I need to do that in okay? Is that you get it, right? I'm trying to use the result of the central limit theorem, which now we know. Okay, we can now approximate by using the central limit theorem, right? We can say that this guy here is if n is large enough, we can say that this guy has a standard normal random variable, right? Okay, so okay, you follow me? Right, okay. Any questions, feel free to give a shout. Now, you can write this probability as the difference of these probabilities okay? And finally, I'm going to use the notation capital Phi. Remember, capital Phi is the notation for the CDF of a standard normal variable, right? I'm sure you know that, right? So using this notation, you can write this as yeah. So that completes example 1. Are you okay with this or no? Come on, guys, talk to me. Are you okay? Yeah. All right. The next example I'm going to look at so let me put this here. So you should oh, it doesn't work. Does it work? No. It's okay. It doesn't work now. I don't know why. Anyway, okay, let's example 2. right? This is the question, example 2. So where S squared is the sample variance, I'm going to use, remember that I gave you two definitions of the sample variance, but in this example, I'm going to use the unbiased version, which is this one here. Right? Okay, now how can we do, okay, in order to do this question, I need to use the result from these notes here. Remember, one of the things that I talked about in the chi-square distribution is this one. I don't know if you remember this result here, right? That is the sum of the deviations of the sample mean has this distribution, right? So I'm going to use it, right? So let me show you how to do it. So this probability, you can write it like the probability that A okay, like this, right? The next thing I'm going to do is I'm going to multiply everything within the brackets by n minus 1. So you get yeah. All right. Now using the result on the side screen, we can say that this guy here, right, using what we say it has the following distribution. It has sigma squared, which is 1, right? Sigma squared is 1 times chi squared sorry, I don't have COVID, don't worry. Right? Okay. You see what I've done? I have used property number 3. So I used property 3 here, right? Okay. So now okay, let me show you what happens here. Now we have 2 points, this point and this point, and the area between them between these 2 points is 95%. That is this area here. The area between this point and the area between these 2 points is 0.95. In other words, 95%. 95% of the total area. So that means if this area is 95%, these 2 areas here should make up 5%, right? Okay, so one way, I mean, there's no unique way to do this, but one way you can do this is to make up, let this area here, let it be equal to 2.5%, right? And let this area here be equal to 2.5%. So the total area is 100%, right? Now, look at the using the percentile, I just talked about a few minutes ago the definition of a percentile. Now, what would this be? According to the definition I gave you, what is the percentile corresponding to this point B? Remember, this is 2.5%. So what is the area below this? If this is 2.5%, the area below this is 97.5. Yeah? You follow me? Yeah? So this point here should be Are you with me? This point must be equal to the percentile that corresponds to the probability of 0.975 to the right. Okay? And similarly, this point here must be chi-squared 0.025 n minus 1. Do you see why? Because the area below this point is 2.5%. So the probability is 0.025, right? Okay? So what I'm saying is that this guy here and this must be equal to this, and this must be equal to this, right? So basically, I'm saying that n minus okay, yeah, so which implies that A must be equal to 1 over n minus 1 times the chi-squared, the percentile of chi-squared at 0.025, right? And similarly, n minus 1 times B right? Okay, so that answers, is that clear, guys? So this is the answer to question example number 2, right? You okay? Any questions, guys? Feel free to shout, give a shout. All right, okay. All right, the next example I'm going to look at is example number 3. All right, so in this example, I'm going to use what we talked about in this slide here. You may remember. Let me go down to this. Yeah, this one here. You remember this guy here. There is property number 4, which says that if you have a random sample from a normal distribution, with parameters 0 and sigma squared, then this guy here, x bar is the sample mean divided by s. S is the sample standard deviation divided by root of n has the t distribution with n minus 1 degree of freedom. So in order to work this probability, in order to work this probability, first you can write it like the probability that x bar divided by s less than 1. Okay? Then you write this as the probability that x bar divided by s divided by root of n, and you need to do the same thing on the right hand side. Okay, right? Now this is the probability that because of property number 4, which is this one, right? This guy must have a t distribution with n minus 1 degree of freedom, and this guy here is equal to root of n. Yeah. Okay. So this becomes the CDF. This is the common notation I will use throughout the course. So this guy here denotes the CDF of a t variable with n minus 1 degree of freedom. Right? It's just a notation, denotes the CDF of a t variable with n minus 1 degree of freedom. So this is an easy example. Are you okay with this, guys? Yeah. Yeah. All right, and so the final maybe I will have more time, but this is example example 4, right? Okay, let x be a chi-squared variable with a degree of freedom. Show that the expectation of x is equal to, I mean, you probably did questions like this in probability 1. I don't know. Did you guys have? Okay, let me show you. This is the chi-square distribution, right? One of the properties I gave you here, if x is a chi-squared variable with a degree of freedom, then the expected value of x is equal to a, right? Now, how would you show this, guys? If I ask a question like this, how would you do it? Remember, the expected value is defined as because this is a continuous distribution, is x times the density function. So for the density function, come on, this is the density function of chi-squared, right? So it's 1 divided by gamma function. By the way, I assume you know what a gamma function is, right? Or you don't? If you don't, let me know. There's a video on gamma function which you can find on the course webpage. I will show you in a sec. I will show you. This is the density of the gamma function of a chi-squared variable with degree of freedom a, right? Now this you can write as the integral from 0 to infinity of x power a over 2 e of minus x by 2 dx, Right, now to work out this integral, well, there are various ways you can do it. One way is to make a substitution. So this implies that x is 2y. So dx is equal to 2 times dy. Let's put this in a box. Yeah. And then if you do the sub back into the integrand, this will become x will become 2y, x by 2 will become y, dx will become 2 times dy. Okay? Now, you can pull out the 2 here and the 2 here outside, so you get 2 to the power a over 2 plus 1 divided by and then you have the integral from 0 to infinity of y to the power a over 2 e of minus y dy. Right, this is why you need to know the gamma function. If you don't know what it is, you should go to the top of this course web page. There is a video about, this is the video that you can watch about the gamma function. Well, I'll just look at the, it gives you the definition. It gives you the definition of a gamma function, which is this one here on the top, right? All right, using the definition, you can write, these two cancel out, so this is 2 divided by right? This is using the definition, right? On the very top equation on this slide here, right? Now, one property of a gamma function is that gamma at a plus 1 is a times gamma at a. This property here, can you see this? Gamma at a plus 1 is a times gamma at a. So you can write this guy here, the second term here, as a over 2 times gamma at a over 2. So these two guys cancel. So the final answer is a. So that's what we wanted to show. We wanted to show that the expected value of chi-squared variable is equal to a. And similarly, you can find the variance. I'm not going to do that. But we still have time, so I will do one more example, unless you're tired. I hope you're not. One more example, example number 5. Some of you said that I'm not doing enough examples, but I mean, the course website has many, many examples. Like, if you go back to the course website, it has tons of examples that you can practice on. Like, let me show you. Like these are the quizzes from, oh, excuse me, why? All right, these are the quizzes from 2018, 18, 19. So there are 10 of them, and there are 10 more from 1920. There are 10 more from 2021, and then there are the final exams and the solutions from 2015 to the last year. So you have plenty of examples you can practice on. So don't, I mean, if you want further examples, I can give you. I mean, I'm happy to give you further examples if you really want them. But I mean, but the course website has many examples that you can practice on, right? Okay, anyway, the example, example 5, okay, let x be a t variable with degree of freedom a. Show that the expected value of x is 0, right? So in order to show this, once again, you need to Because remember, the density for the t variable is this complicated function, and it's defined from minus infinity to plus infinity of x times so you need to show that this integral here is equal to 0. Now, I have time, so let's pull out this constant here outside. So you have then you have the integral from minus to plus infinity of x 1 plus x squared Yeah. Now, how do we show that this is equal to 0? Any ideas? Huh? Come on, guys. All right. One idea, well, it's kind of obvious because of symmetry, but I mean, one way to do this is like this: is to split the integrals into two integrals. All right, and then for the second integral, for this integral here, set y equal to minus x, right? So that x is minus y, dx is minus dy. All right, so if you do this, this is what you will get. I'm going to kind of rush a bit because I'm running out of time, but all right, if you do this for the second, if you do make the substitution that okay, let me put this in a box so that it's kind of clear. If you make this substitution for the second integral, right, this is what you will get. You will get this to be equal to minus 0 to infinity of y all right? And these two integrals are the same, so they do cancel out. So this is equal to 0. You follow? Yeah, I'm sure you guys are experts in calculus. I mean, you did calculus only this year, so you should know how to do this. Right? So you should make this substitution into the second integral. It will become equal to this. And these two being the same, they cancel out, and therefore the expectation is 0. Right? Okay, guys, so by the way, if you haven't been to any of the tutorials this week, there is one this afternoon. Shh. If you haven't been to any of the tutorials, there is a tutorial at Friday 2 to 3 in the computer cluster. So please come to the tutorial from 2 to 3 today if you haven't been to any of the tutorials. Now next week we have these tutorials, These are the tutorials for next week, and they will be based in this problem sheet here. This is the problem sheet for next week. So please try to have a look at this sheet before you come to the tutorials, right? Okay, guys, so have a good weekend. And any questions, as usual, please feel free to contact me 24/7, right? Bye. See you. Yeah. I put a scanned version in the course website. You can see it. You don't have to write down everything. Yeah.
Of this?
Yeah, I scan everything and post it, upload it to the course website. Yeah, up there. Yeah.
I'll ask a question.
Yes.
Yeah,
Which question? This one? Or this one? Example 3? Or example 2?
Yeah, sir. I don't understand why is it x squared? It's a multiply 0.025.
No. It's just called x squared. Yeah, it's a notation. It's just a notation for it, sir.
And sir, why is x squared equal to n times n minus t times n minus 1?
No, not times. Not times. It's not times. It's just a notation for the chi-squared variable.
And what's mean by t?
T is a student variable. It's a random variable. Like here, this is a random variable. This is a random variable with degree of freedom. Sorry.
No, that's all right.
It's a random variable. Random variable with n-1 degree of freedom. You shouldn't take this as multiplication. It's not multiplication.
It's a t the distribution.
Yeah, it's a distribution with n-1 degree of freedom.
So what's the function for this distribution?
Huh?
I mean, what's the identity function?
I showed you earlier in the class, right? When I talked about it. This is the density. This is the property. This is the PDF of the student T, and these are the properties of the student T. Yeah.
Yeah, I see, sir.
Did you not watch the videos?
Yeah, I do, sir. But I'm just really confused. Yeah. Well, I understand.
A little confused. Come to my room. I'll explain.
Yeah, sure.
You're in Alan Tony, right?
Yeah.
So come and see me. I'll explain.
Thank you so much.
Yeah.
Sorry,
Yeah.
I was just going to ask you how to make this work, but it seems to work.
Yeah. Okay. So
Do you not use the?
No, I don't use those.
Yeah.
I use the one here.
Oh, that
Yeah,
one.
I don't
Yeah.
use it.
Yeah. Okay. Oh, there's a second visualizer. Isn't the second visualizer?
I suppose to do,